power of prime p in n factorial using the concept of this greatest integer function, and in this class I am going to prove this particular Hermite identity, which helps you in many cases, okay, not only particularly in this step function related questions, okay. See, related to this Hermite identity and related to this greatest integer function, there are some questions in calculus part also, okay. In all those cases easily we will solve if you are aware about this Hermite identity. Just look at the statement once again. Step x plus step of x plus 1 by n plus step of x plus 2 by n plus and so on plus step of x plus n minus 1 by n plus is equals to nx, where if you go for the restrictions, x is any real number and n is any natural. You just think, observe it, okay. X is any real whereas n is any natural, or you may say whole number, because here x plus 0 by n, right? So you may say natural or whole number, okay, as per the situation, no problem. Okay, right. Yeah, and then to analyze it, to prove it, what we need to do? First of all, x is a real number. Since x is a real number, that x must contain an integral part and fractional part, okay? As given, x is a real. Since x is a real, x must contain some integral part plus fractional part, okay? And we know that for I an integer and f is a number which is in between 0 and 1, okay? 0 less than or equals to f less than 1. We know it, right? And from that it is very clear that what you know, step x is equals to I, because it's the integral part, step x is equals to I. Okay. But we need to think about step of x plus 1 by n, step of x plus 2 by n and so on. That in the sense, we need to think about step of x plus k by n. Okay, we don't know its value exactly. First of all, we need to think about the step of x plus k by n for k is equals to 0, 1, 2 and so on n minus 1. Is it right? So x plus 0 by n is the first term, x plus 1 by n is the second term, x plus 2 by n is the third term, and x plus n minus 1 by n is the last term. So what is its value? First of all, we need to think about it. And after identifying the value of step of x plus k by n, we need to prove this Hermite identity. Okay? So just look there, step of x plus k by n. Here the values of k are from 0 to n minus 1. Since the values of k are from 0 to n minus 1, what you say about the value of k by n? If you think about k by n, k is a number which is from 0 to n minus 1 and that n is clearly a larger number. So, smaller number divided by the larger number is always less than 1. And if you take k as 0, it may be equals to 0. And for all the remaining numbers, this k by n value also lies in between 0 by n. So, since we are thinking about x plus k by n, for k is equals to 0 to n minus 1, and from these values clearly k by n is again a number which is in between 0 and 1. Yeah, now what you say about its value? Now just think about this step of x plus k by n value, and that is equals to step of x is what actually? X is some integral part plus fractional part, and that fractional part is again a number between 0 and 1. So integral part plus fractional part plus k by n. Okay. Yeah, what you say about its value? See, now just have a look. F is a number between 0 and 1. K by n is also a number between 0 and 1. F is a number between 0 and 1. K by n is also a number between 0 and 1. If you add these two, f plus k by n is a number between 0 and 2. That means if you add this f plus k by n, we don't know whether the value is less than 1 or greater than 1. Okay? Because 0 plus 0 is 0, 1 plus 1 is 2. So here we have, if you think about this f plus k by n, we have two possibilities. In one case, f plus k by n value is less than 1. In the other case, this f plus k by n value is greater than 1. And in particularly, in the first case, f plus k by n value is in between 0 and 1. In the second case, f plus k by n value is in between 1 and 2. Okay, f plus k by n is less than 2. Just think about it. I have two possibilities related to this f plus k by n. I is clearly integer, that was clear. Okay, and now you just think about this f plus k by n. If this f plus k by n is in between 0 and 1, this f plus k by n just acts like an integral part. So at this position, the value of this step of x plus k by n is directly I. Whereas in the other case, if you think about where f plus k by n value is in between 1 and 2, in that case if you think, since it is between 1 and 2, you have a chance to rewrite this f plus k by n as 1 point something. So I plus 1 point something, then it results out like I plus 1. Just think about it. So what my conclusion is, if you observe this step of x plus k by n, it has two possibilities. In one case its value is I, in the other case its value is I plus 1. It is I if f plus k by n is less than 1, and it is I plus 1 if f plus k by n is greater than 1. Once again I am repeating you. Yeah, the problem is related to the step x and x plus k by n format. For suppose you just take step x is equals to I and x is equals to I plus f, and then we need to think about step of x plus k by n. So while thinking about that step of x plus k by n, what you say about k by n? K by n is also a number between 0 and 1. So when you combine these two, f is in between 0 and 1, k by n is also in between 0 and 1. Therefore 0 less than or equals to f plus k by n is less than 2. This f plus k by n value is in between 0 and 2. Since I need x plus k by n, I plus f plus k by n, here I have f plus k by n. So since it is from 0 to 2, split into two parts. F plus k by n if in between 0 and 1, f plus k by n if it between 1 and 2. If it is in between 0 and 1, so this is the decimal part, like 0 point something, neglect it, its step value is directly I. Whereas if it is in between 1 and 2, so 1 plus some fractional part, that 1 get attached to this I. We need to add that 1 for this I, and that's its step value I plus 1. Just now we found the possible values for x plus k by n. After this analyzation, now we are easily prove this Hermite identity. First of all, just think about it, and then I will start the left side part and the right side part. I proved everything. Okay, just have a look. Yeah, just have a look. So just now we have x is equals to I plus f, x plus k by n is equals to I plus f plus k by n, and step of x plus k by n has two possibilities, I or I plus 1. Here this is the left hand side, and in this left hand side totally there are n terms starting from 0 to n minus 1. See, every value is either I or I plus 1. We have two possibilities. So since the values are continuously increasing among these n terms, for some terms the value is I, and for the remaining terms the value is I plus 1. We need to break it where up to which it is I and after which it is I plus 1. So I am just rewriting it like this. Just have a look. This is equals to step x plus step of x plus 1 by n plus and so on plus step of x plus p minus 1 by n, okay, plus step of x plus p by n plus and so on, which is step of x plus n minus 1 by n. We need to analyze it. Okay, somewhere there is a number p. Okay, I break that situation. Totally there are n terms. Just I am breaking that. How many terms are there here? See, starting from 0 to p minus 1, these terms are p terms. Okay, and totally n terms. Since they are p terms, and these remaining terms are n minus p terms. Okay, and as per my discussion, every value is either I or I plus 1. You just consider, you just imagine, for the first p terms it is I, and for the remaining terms it is I plus 1. Okay, see, every value is either I or I plus 1. First one is I, second one is I, third one is I. For some terms it is I. After a certain stage, the value becomes I plus 1. We don't know up to which it is I and after which it is I plus 1. So you just treat it like some p. For p terms it is I, and for the remaining n minus p terms it is I plus 1. If you treat it like that, so every value is I for the p terms, so you just take its value is pi, because I need to add for p terms. And after these p terms, the remaining n minus p terms, the value you just, it is I plus 1. So I plus 1, I plus 1, I plus 1, and the number of terms are n minus p into I plus 1. Okay. Here just I am breaking the total summation into two parts. Terms having the result as I, terms having the result as I plus 1, because we have only two possibilities. For first p terms the result is I, and for the next n minus p terms the result is I plus 1. So you just try to simplify it. Pi n minus p into I plus 1, ni plus n minus pi minus p, and this pi and pi will get cancelled, and you left with what? Ni plus n minus p. You just observe it. Okay. I started my discussion with the left hand side. On simplification of this left hand side, the result is ni plus n minus p. Okay. So this is left hand side. And then now I need to prove the right side also. That means step nx also as this ni plus n minus p. And to prove that I need some information. That information I collect from this division. Okay. See, just look there. What I mentioned to you here. See, I am erasing this because we know all this information. Yeah. This is left side. After that I will prove the right side. And before proving the right side, I will think about these two terms. Okay. See, just think about it. This x plus p minus 1 by n step value, I consider it as I. Okay. Here, yeah, just think about it. Step of x plus p minus 1 by n, I considered it as I. Okay. Yeah. What is x? X as per the discussion I plus f plus p minus 1 by n is equals to I. You just think about it. Since its step value is I, this fractional part must be less than 1. Okay. And that's why that implies f plus p minus 1 by n is less than n. Not n, less than 1. If this fractional part is less than 1, then only I will get the step value as I, right? So, and if you simplify, multiply everything with n, nf plus p minus 1 is less than n. Just think about it. And you send these two terms that side. I have that nf is less than n minus p plus 1. Just observe it. Nf is less than n minus p plus 1. If I treat it as I. Similarly, if you take this term as I plus 1, you will get the similar type of expression. There you will get that nf is greater than n minus p. You will get that nf is greater than n minus p just by taking this term as I plus 1. You just try for that. Take that step of x plus p by n as I plus 1 and then find that nf greater than n minus p. Okay. Try it. Just look at the board once again. Okay. This is the left side. We are proving this. Okay. Step x, we have n terms here in the summation. So I just break those n terms into two parts. First p terms, remaining n minus p terms. So the value of first p terms, every value is I. So I for p terms it is pi. And for the remaining n minus p terms, the value is I plus 1. I plus 1 we need to add for n minus p times. So n minus p into I plus 1. Okay. So pi n minus p into I plus 1, simplify, on simplification you have that ni plus n minus p. This is left side, the left side is completed. So the simplification of left side is ni plus n minus p. Ni plus n minus p. Okay. And now I need to find this right side value also as ni plus n minus p. So to find it I am thinking something. Okay. So in my discussion, in my thoughts, see, just think that these two are the extreme positions. Its step value is I, whereas its step value is I plus 1. So its step value is I in the sense x is I plus f plus p minus 1 is I. So its step value is I. So this fractional part for sure is in between less than 1. So since it is less than 1, we have nf less than n minus p plus 1. Okay, so this is required for the right side part. To prove the right side part, I need some information, and for that I am doing all this. Okay, Left side part is completed, it is ni plus n minus p. And to prove that right side also has ni plus n minus p, I am working. So on my work, its step value is I, its step value is I plus 1. It's I plus 1, right? So since it is I plus 1, I will get the second part. I will do now for you. Just have a look. Yeah. So if you take that, see, if you take that, step of x plus p by n is equals to I plus 1. Then what you have to do? Step of x plus f plus f, x means I plus f, right? I plus f plus p by n is equals to I plus 1. I is the integer. F plus p by n is the fractional part. If this fractional part is less than 1, you get your step value as I only. But here I plus 1 is there. That means this fractional part f plus p by n is greater than or equals to 1. Now multiply with n. Nf plus p is greater than or equals to n. And then nf is greater than or equals to n minus p. Okay. That's I wrote here. Okay. So if this is I, we have one statement. If this is I plus 1, we have another statement. And I am going to combine these two. Just look there. Nf value is less than n minus p plus 1. Nf value is greater than n minus p. From these two, if you combine, n minus p is less than or equals to nf, which is less than n minus p plus 1. Think about it. N minus p is less than or equals to nf is less than n minus p plus 1. So what you say about this step of nf or something? So this is the information what we have in our hand. Okay. Now think about the right hand side. What is the right hand side? Simply step nx is the right hand side. So that is equals to step of nx. What is n? What is x? We know that x is equals to I plus f, right? So n times of x is I plus f. Okay. And that is equals to step of ni plus nf. Okay. And this ni is an integer, nf is a number which we don't know exactly. So you need to write it like ni plus step of nf. And this nf is a number which is in between n minus p and n minus p plus 1. As per our discussion, n is a natural number, p is also natural because p terms and n minus p terms we are mentioning. That means p is also a natural. So n minus p is a natural number. Nf is in between n minus p and n minus p plus 1. Two consecutive numbers. So step of nf is n minus p. So this is equals to ni plus n minus p. Just look there. Previously, left hand side on simplification we have this ni plus n minus p. And now right hand side is also ni plus n minus p. At the end, both left hand side and right hand side are balanced. So the sum of these n terms is equals to step nh, and at the end this is Hermite identity. Okay, just have a look. Just look at the board. We have three problems, 10a, 10b, 10c, which we can prove using Hermite identity. First of all, think about the first problem. Okay, step of 1 by 4 plus, step of 1 by 4 plus 1 by 200 plus and so on plus step of 1 by 4 plus 199 by 200. So when you compare with the given one, your value of n is 200. Okay, 1 by n, 1 by 200, 2 by n, 2 by 200, like that, n minus 1 by n, 199 by 200. So and x value is 1 by 4. So you need to take x is equals to 1 by 4 and n is equals to 200. So its answer as per Hermite identity, step of 200 into 1 by 4, because step of nx, right? Step of 200 into 1 by 4 on simplification, which is 50. So if you add all these step values, your answer is 50. There ends using Hermite identity. Is it clear? Right. And then you need to think about the next one. Step of x by 2 plus step of x plus 1 by 2 is equal to step x I need to prove. So that's also very simple part actually. So first of all, you just remove this right side and then start your proof. Okay. Yeah. I will rewrite it like this. This is equals to step of x by 2 plus step of x by 2 plus 1 by 2. Is it right? So it has only two terms. since it has only two terms and first value is x by 2. Just like x, we have x by 2. Just like n, we have 2. N minus 1 by n means 2 minus 1 by 2 means 1 by 2 only. So adding these two terms using Hermite identity is simply nothing but taking 2 in the place of n and x by 2 in the place of x. So at the end its answer is nothing but step of 2 into x by 2 by Hermite identity. And its value you will get at the end as step x. Just think about it, okay? Just have a look once. So the second bit, step of x by 2 plus step of x by 2 plus 1 by 2. And to apply Hermite identity for these two terms, n is simply nothing but 2 and x is x by 2. Okay, in the place of x, treat x by 2 as your x. So nx, 2 into x by 2 is step x. So b bit is also completed. And now using this b bit, we need to prove this c. Okay, so Hermite identity, it's a direct example. And using Hermite identity, this is another wonderful example, and based on that we can prove this C. I will erase everything for the space and I will start proving this C. Okay, just have a look. At the end, so now our intention is to prove this 10C. For that, I will utilize this step of x by 2 plus step of x plus 1 by 2 is equals to step x. Okay, right, using this I will prove, or you may use some different variables, maybe step of n by 2, okay, or you may say step of y by 2 plus step of y plus 1 by 2 is equals to step y. Already we proved it using Hermite identity. Now for this, first of all take y is equals to x. In this place take y is equals to x. What we have? Step of x by 2 plus step of x plus 1 by 2 is equals to step x. Okay. And next in the place of y, you just take x by 2. We have this statement and use x by 2 in the place of y. If you use x by 2 in the place of y, x by 2 by 2, that will become x by 4 plus x by 2 in the place of y, x by 2 plus 1 by 2. You just try to simplify. Replace y with x by 2. X by 2 plus 1 by 2, which is simply x plus 2 by 4 is equals to step y. Y is x by 2, right? So this is what? Step of x by 2, right? And I am going to prove that step x is this infinite summation. This is infinite terms you can get. Okay, approximate value is step x, and that's what I am going to prove. So in the next step, you just take y is equals to x by 4. Now what you will get? Step of y by 2. And what is my y? X by 4. So you will get that x by 8 plus step of x by 4 plus 1 by 2. So on simplification you will get that x plus 4 by 8 is equals to this side you have step of x by 4. Okay, likewise I can take and the next x by 2 and then I will proceed. And now you just add everything. You just start with this step x. Okay, step x is equals to step of x plus 1 by 2 plus step of x by 2 from this first statement. Now replace step of x by 2 as this in this step x by 2. If you replace, what you will get? This is equals to step of x plus 1 by 2 plus this x by 2 is sum of these two terms. First write it, step of x plus 2 by 4 and then plus step of x by 4. And again replace step of x by 4 with this summation. Likewise, if you continue at the end, you will get that step x is approximately equals to the infinite terms step of x plus 1 by 2 plus step of x plus 2 by 4 plus step of x plus 4 by 8 and so on. We need to continue further. Okay, so it's here you will get infinite terms. Okay, here you will get infinite statements. On adding all those things, on combining all those things, we have this particular statement. Okay, it's also an example of the Hermite identity. So in 9th point we discussed about Hermite identity. In 10th point some problems related to the Hermite identity. Just have a look.